So now that we have this t-distribution to work with, and that we know that it's got some formula for how we get sampling means on it and show how it curves like a normal distribution, we can use it exactly the same way like we've used our other distributions for getting a p-value and for getting a confidence interval. So we can do that, but it has assumptions, and here's where simulation is great and where the formulas start to run into more trouble. In order to use a t-distribution, we need to have a sample size that's larger than 30. That's where the central limit theorem comes in. The central limit theorem works and allows us to use these different distributions without simulating anything when either the sample size is large enough, greater than 30, or the underlying population is normally distributed. And, how do we know if the underlying population is normally distributed? Well, we generally don't, but if the data are normally distributed, then that's a pretty good sign that the population is probably normally distributed. So we either say our sample size is greater than 30, or our data are clearly normally distributed. That's why we look at and describe data before we do anything. And then we can go and use a t-interval. If the sample size is too small, or if there's some kind of skew to it, if the sample size is too small and there is some kind of skew to it, we use bootstrapping. Bootstrapping can do the job for us. But yeah, again, if it's a small sample, but it's nicely normally distributed for the most part, symmetric and bell-shaped, then we can go right ahead and use a t-distribution and use our formulas for calculating things here. And I really want to emphasize again, you're not going to have to calculate any of these things by hand. There's some formulas here to show you where the different pieces come in for using these things. But in this class, we focus on the practical side of things, so you use the software. Again, I guess, yeah. This is extremely similar to what we just had with the confidence interval using the normal distribution and the z-score. Instead, it is our statistic for a confidence interval, just like before, sample mean, sample proportion, plus or minus some multiplier times the standard error. That multiplier, instead of coming from the z-score, the z-star, the normal distribution, instead it's going to come from the t-distribution. So it will be some t-score or t-star as we have here. Okay, so how do we find our multiplier? Again, we've been using about 2. And for all intents and purposes, 2 is fine. 2 really is a good estimate. But let's say we want to be exact, and we want to know the exact multiplier we need to get, for example, 95% confidence. Okay, here's the thing. You can get a t-distribution in StatKey, and you can, again, do this idea of how much of this distribution, how much of this width is contained between certain bounds. The t-distribution changes depending on the sample size. Again, because we're not working with the population and we don't know the population standard deviation, we have to estimate things. We are working with uncertainty. So a different sample size gives us a different shape to our t-distribution. Okay, so we find our degrees of freedom to tell us what specific shape of t-distribution we're working with. And for a single mean, the degrees of freedom is simply the sample size minus 1, or n minus 1. So for the case of a sample size equal to 50, that's 49 degrees of freedom. And if you plug that into StatKey and look for 95% of this t-distribution with 49 degrees of freedom being covered, then that gives us a t-star of 2.01, or very close to 2, like we've been using before. So hopefully you're starting to see this, and that it makes some sense that we're covering about the same area under the curve for the normal distribution, for the bootstrap distribution, for this now these different t distributions. It's all the same thing. So anytime you need to find a confidence interval, you need to find what t distribution you're working with based on the degrees of freedom. You need to figure out what your multiplier is on this standard error to find out how far above and below our sample statistic to go to get the confidence interval. So let's do an example. Our body temperature example. We've got a sample size of 50, a mean of 98.26, and a standard deviation from our sample of 0.765. That's all the information we need to work with. Let's use the formula. Let's use what the theory allows us to do. Let's say we want a 90% confidence interval for the average body temperature. So there are some things to check on first. If you go into the stat key and look at the t distribution, and you say, give me a t distribution with 49 degrees of freedom at 90% confidence, it will give me a multiplier of 1.677. So going up and down 1.677 will cover 90% or 0.9, the proportion of this whole t distribution here. So that's what I want for my confidence interval. I want to cover 90% confidence. All right, so what's the formula I use? Well, I use the sample mean body temperature, I use my multiplier, and then I use my formula for the standard error. Again, we're not simulating anything, so I don't simulate a standard error. There are formulas that allow us to calculate it. And so it's the sample standard deviation as divided by the square root of n. And these are the numbers. 98.26 from before, 1.677, which we just found now, and 0.765 for the sample standard deviation, and 50 for the sample size. Plug all those numbers in, and we get a 90% confidence interval of about 98.08 to 98.44. And the interpretation is the same. 90% confident, average body temperature for this population is between 98.08 and 98.44. The only real difference we're doing here from the bootstrap distribution is that we're using formulas to calculate the standard error, and we're using this theoretical t distribution to give us our multiplier. So we're not just going up and down 2, we're not just picking percentiles. We're using some exact theory and formulae here to get to this. And again, you're not going to have to do this by hand. You won't have to calculate this. This is just how it works. This is just where it comes from. You'll see the examples in the next video of how to do this in StatCrunch. Okay, so that was a confidence interval for a single mean. As a quick addition, what about a interval for a difference in means? Well, if we want to find a confidence interval for a difference in means, like our PISA test scores, for instance, well, we need a sample. Again, we need a sample size that's large enough for the central limit theorem to work. In this case, we need both of the samples we're working from. Remember, a mean difference means there's basically 2 samples we're working with because we're subtracting one from the other. So both samples need to be greater than 30, or both samples need to basically be normally distributed. That's the long and the short of it. Greater than 30 for both, or both normally distributed. If neither of those are satisfied, then we use bootstrap. Or for small samples, you can still use bootstrapping to be safe. I won't belabor that point. A lot of this is just repeated. Okay, a formula thing you're not going to need to use, but just so you see how it works. The standard error for our mean difference is about this here. So it's just this formula involving both sample standard deviations and the sample sizes from each mean. And these are just formulas you can read and use, but you're not going to use it in this class. But that's how we calculate theoretically the standard error to estimate the sampling variability for our 2 samples situation, our mean difference situation. So this looks like a whole huge honking mess, but again, it's just the same formula that we've used before. It's the statistic of interest plus or minus some multiplier times the standard error. In this case, for our parameter of the first population minus the second population mean, we just have our statistic of the mean difference of the samples, our multiplier of our t star, and then the formula for our standard error. Here's a thing, though, that happens. We've got two samples. We've probably have two populations. There are some theoretical things that need to be considered as to whether or not we consider the variances of each of these samples to be the same in the population. So mathematically, if you check an option called pooled variances, it assumes that both populations have the same standard deviation. That's not always true. So there's an option to say we unpool the variances, or we say that the two variances are basically the two standard deviations. The two variances or the two standard deviations are different between these two populations. So we use what's something called unpooling, and that gives us some more flexibility in our calculation. And you will uncheck that in the software. I will show that to you when we get there. So we will use unpooled variances for our purposes. So remember we use degrees of freedom for our t distribution, picking the one we need. When we are doing a mean difference, our degrees of freedom can be really complicated, and I'm not going to get into it. That's a whole separate idea and consideration to consider. So the really conservative thing to do is just to take the first sample minus 1, the second sample size minus 1, and then just pick the smaller of the two and use that as our degrees of freedom for picking the t distribution that we'll use. That's a conservative way to do this, and it's perfectly fine and safe. And again, in this class, we're using unpooled variances. Again, that's an option you'll check. It's a certain assumption. It changes the math going on behind the scenes. Okay, that was confidence intervals. There really isn't much more to say for the hypothesis testing. It's the same thing. We're using a t-distribution, but now we're just using slightly different information from it. Again, it's the same with intervals. We've got to have when we're testing something, we've got to have a sample size greater than 30 for any sample we're working with. Or they must look reasonably normally distributed from the sample. That's pretty straightforward. And if they don't hold up, then we use a randomization test. Again, if we've got a small sample size or things look symmetric, we can just use our simulation method. That's perfectly fine. But for one mean, for difference in means, these conditions have to hold across all the samples we're working with in whatever thing we're analyzing. Again, sample size greater than 30 in all samples we're working with, or the sample looks reasonably symmetrically and bell-shaped in its distribution. If not, randomization test. So here's where it's a little bit different. We get our p-value from the t distribution. We get our p-value by converting our sample mean to the t-score that will go on the t distribution. And we look at the area more extreme than the t-score we compute from our sample statistic. How do we get the t-score that we're going to use to find out what is more extreme than that, and in what proportion of the t distribution is more extreme than that? We just say, give me my sample mean, subtract out the null population value of interest, and divide it by this measure for the standard error, this formula for the standard error for my sample. This gives us a t-score that we plop on our t distribution, and we say, how far away is that? Give me a p-value. Give me the proportion of the t distribution that's at or beyond this t-score. It's just like the randomization distribution, except we're not simulating anything. We're just starting with the distribution. We already know it theoretically, and that's the t distribution. And we pick that exact t distribution again using n-1 degrees of freedom. Nothing new there. Okay, so I'm at the tail end of this video. So what I'm going to do is I will pick up with this body temperature example, and then finally go through these last examples in StatCrunch to show you how this works, and then that will round out this series of videos. So, okay, on to the next video.